All right, I'm pleased to hear it. All right, welcome to the slightly early sync to the national face, that little black area in the LCD on my watch face that says that I'm now synchronized. So I'm going to blather for 6 more seconds so that we can claim either precision or accuracy. You can have one or the other. And then there's this related thing about the Heisenberg uncertainty principle. What does it mean? I'm not sure. Oh boy. This reminds me of the time that Chuck Morgan's computer Windows updates scant seconds before his talk. So welcome to the Silicon Valley Fourth Interest Group. I'm Kevin Appert, program chairman, and we have a good program scheduled this afternoon. Last minute, so it won't be on your agenda. Maybe it'll make it to the meeting notes after the fact. Who knows? I wanted to talk about FranLab. This is my new FranLab shirt. FranLab is a YouTube webcaster. She does relatively frequent YouTube bits about electronics and technology, and she's interested in the Apollo, the space program, electronics, the computers, and so forth, and other stuff. So I recommend her website to you. Have a look at it. It's great stuff. One of the things that to us is that she sells these. There's a website that does like T-shirt fundraisers, and it's organized in that way for fundraising. So if we ever do another round of T-shirts, this may be a viable thing to consider. And I see Brad is completely uninterested in any of this, so it's unlikely to happen. So the folks at Fry's Electronics in California, I don't know, are there any stores elsewhere, have unusual decor in their stores. Each store has a theme. This is the Fry's store in Fremont, California, where they have a exciting, honking big Tesla coil, which is a model, a reproduction of one that Tesla actually built. And boy, that's impressive. So this may become a series here at SVFIG, where each month we look at a new Fry's store and look at their decor. So anyone else? Rumors, gossip, announcements, slander, libel, blather? George?
Yeah, I heard folks got headhunted and such. Look, there's so much, blah, 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 politics and religion. I'll say this. If Bill Hicks had not caught a mysteriously rapidly advancing pancreatic cancer, he'd have had to got hit by a car coming back from his honeymoon like Sam Kinison. In another wildly unpredictable death. I'll tell you, fine brains are, it's a big risk factor in this land.
Anyone else? And Ting.
Yeah, I'm still working on the air robot, the full system for it, and the ESP32. Okay, ESP32 fourth is coming along, and I think I just got the flash memory to work.
Woohoo!
Yeah, so that I can externally load a text file into the flash memory, and when the fourth is booted up, you will read that text file into memory and actually compile.
What kind of flash memory is it? Is it like a USB or inside on the chip?
The
all right.
SPI. flash.
Uh-huh.
So it's already in, on the chip. It has 4 megabytes of it, 4 megabytes of memory. And it's very nice if we can, Forth can use that memory to store some applications upon boot. It will load that file and boot this, compile the application. This way, I can separate the Forth core with the application. And so I think that I will put the robot code into a text file and load it up. I think that will make it the Forth a general purpose kind of thing.
That sounds exciting. I can hardly wait to hear about that. Are we progressing towards a Maker Faire event, or? Well,
Talk about his robot.
okay.
You can pre-purchase Maker Faire tickets starting today.
And where would one go to pre-purchase Maker Faire tickets?
Online.
On the interwebs. Okay, that makes sense.
So I put in the application.
And you'll let us know when you get some feedback. Okay, great.
We'll get the booth. Probably next month.
Sounds exciting. So we may have another SVFIG booth at Maker Faire this year. Yes.
Okay. We unlocked here? That's what's not unlocked. No, that's locked.
Oh, that one's locked over there.
Try to hold it back.
There we go. Figure out where to put that. And I think I should be talking. Let me get over here, make sure I'm talking. Yeah, I'm talking. That one's gonna go that way. We'll just get into A mode. Which spigot do we got? That spigot. Why do we have a bell up here? Where am I? Okay. Now I'm going to get into screen share. Yeah, I guess share the whole thing. And we go over here. And there we have. And Don was supposed to be talking according to the schedule. As Ting mentioned, we were waiting for Don. He hasn't shown, so I volunteered to jump in. And what I have done is taken just with Arduino on the ESP32 and hooked up an SD card. Here we have a accelerometer, a radar, SD card, and the Fire Beetle from DF Robot. DF Robot makes this nice little device that's there. And It's a cute one. There's all sorts of ESP32s, and the fun with them, all the pinouts are different. Every one of them, the pinouts is different. And so that makes life rather difficult with the things. But what they do have, and here's links for the accelerometer and the radar, not involved with the talk, but just happen to be hooked up with what I've got at the moment. This SD card holder, if you notice on the name, it's just a pin conversion because the SD card has real tiny pins. This has the 0.1 center pins, is basically all you've got. And so, okay, that makes it easier to hook up into a breadboard. And there is some information on doing pull-ups standard with the ESP32 and the SD cards in particular. They claim that you've got to pull all the pins up. I only really had to pull one. Didn't work with them all pulled up. Also on my thing, the SD card that I used is 128 gigabyte. But you can't use Microsoft to format it because Microsoft says that if it's bigger than 32 gigabytes, you ought to use NTFS. Fine. You find another utility here. Then, and I'll show, hopefully be able to show all of this in a moment. This is on the Arduino with the Arduino system hooked up, that you go to examples. Once it gets set up for the fire, whatever ESP32 you have, you'll have an SDMC test routine is what I use. Very simple test routine that doesn't do much of anything. It just reads it. You have to get rid of a few, in the test, you have to get rid of these 2 lines of code, obsolete functions. It's the fun part about Arduino is all of their examples have been done one time and the system just moves away from it. And you've got obsolete problems. And then finally, when the thing runs, it does a power up there. Then it starts listing all the files that are on that device. And finally, it does some reads and writes way down at the end. Where'd you go? And that's all it really does. And this was just a quick talk. I don't know whether I will kill everything by doing this, seeing I'm on the same computer, but let's try. Arduino. It's spinning. It takes a little bit to load up Arduino, especially with all the stuff that I've got going on as I'm streaming all of this too. Come on. There we go. And that's the wrong one. And all I really want to do is go into the serial monitor and press reset. And there it runs. And it's reading and writing to the SD card. That's really it. It's as simple as that. My next step in this is getting it out of Arduino into the EP32s are made by Expressive. Expressive has a GCC environment that is just a pure GCC environment. And that's where I'm going next. There I did find the pinouts. Here I can't find the pinouts because I need to change the pinouts for another device that I'm using that's got a camera on it. But any questions? That's it. Now, get out of all of this. Who's next? Brad is next. GCC compiler and make.
Compiler for what language? You say GCC, a lot of people think you mean the C compiler.
C compiler.
These days it stands for Goddamn Compiler Collection.
It is a compiler collection. There is, and I haven't heard of a GCC fourth yet, but should be possible. That's G. That's it's not necessarily G4. They didn't make it into a compiler. Yeah, it is. They use GCC. It is a compiler collection. In this case, most of the stuff is C. I really haven't looked to see whether they're using C++. Arduino is a almost C++.
It's got a user-friendly figure on it, and it looks like a different
Correct.
language, but it is actually C++.
I heard there were some things missing. I'm not sure that it's a full C++, but that's just what I've heard. I have the mic.
From the compiler.
We have a
Alrighty, I'm Brad Nelson, and yeah, then Dennis just spoke, Dennis Rufer, and now Brad Nelson is speaking. Something like that. Okay. Blah, blah, blah. So I'm going to talk a little bit about Forth and Lisp, and in particular, I'm going to use this famous textbook as a sort of a guidepost to lead this exploration. The structured interpretation of computer programs was used for many years as the intro CS course textbook at MIT. Eventually, they dropped it as the course switched to Python, apparently, as one does. But it, for a substantial span of time, formed sort of not merely the sort of programming introduction for a number of MIT students, but it also sort of has a certain philosophy of programming that's interesting to look at. And I recently was looking at it, and amongst other things, noticed it was online and whatnot. So thought, oh hey, let's talk about this. The other thing that's fascinating with it, if you go on sundry MIT websites, they actually have videos of some of the earliest versions of the course. But what they actually have is a recording of an instance in, I guess, 1986, in which the course was given to sort of in a crash course form to a bunch of employees at HP or something of the sort. It's also fascinating, both sort of how dated it is, where there's the slides. They're not quite sure whether they should call it slides or screens or whatever, because they're using very early instance of projected computer slides, and I believe there's a light pen. But in place of a mouse there. But the
but the other thing that's fascinating about it is sort of how much it stood the test of time. That it's actually surprisingly modern in feel. Some of these old videos, but the text has diverged a little from those videos. Originally, I think it started out as course notes and evolved into this form. So a bunch of disclaimers up front. It's a big book, and I'm going to cover some of it. And also, there are many fourths and many Lisps, and the comparisons I'm going to draw are sort of narrow and particular to the things that seemed interesting to me as I was drawing up my slides. I'll also have the caveat that I probably have far too many slides, and will almost certainly skip over a bunch of them. But I figured better too many than too few. The other thing is that I had hoped for some deep insight, but as one often encounters in going through something large and trying out a bunch of examples, you feel like you have enlightenment by trying specific examples, but on the other hand, you may not see the forest for the trees. And the other thing I wanted to emphasize is that I'm not trying to sort of draw some sharp comparison between the two and suggest one is better than the other or something. I'm just sort of trying to illuminate and explore. So yeah, Lisp. It was chosen for a number of reasons for this particular text, and the emphasis is, obviously these are the creators of Scheme, early days were involved, but it's also a pretty good choice for an introductory language. They, over the years, stated many explanations for their choice of Lisp, not least of which they would get in a bunch of freshmen who, I know programming from XYZ, and this was a way to sort of throw something different at them. So it's the book is divided into 5 very large chapters. I'm going to primarily be looking at pieces from the first, second, and fourth chapter. I'll ever so briefly touch on some items in the others, but if I get really ambitious or decide that this was a useful exercise, perhaps I'll revisit the others. In some sense, you'll notice I stuck to all the ones that have the word abstraction in the title. This is not entirely accidental, because these are also the ones where I think the most interesting comparisons kind of pop out. So without further ado, chapter 1. So a sort of the big idea theme for the book overall, but certainly something that they kick off from the beginning, is that there are these sort of key elements of programming languages, and that you would want to look at sort of what are the basic sort of atomic elements of the language, what are the means of combination for those elements, and then what are the means of abstraction. And they, in particular, suggest that if someone is suggesting to you that you might want to consider a given programming language, you should ask, how does this programming language live up to these 3 sort of categories of things? What basic operations does it provide? How can you combine them? And then how can you sort of name the things that you've combined and abstract on top of it? So, well, primitive expressions there's sort of a very obvious literal comparison. There's a bunch of primitive operations in both Lisp and Forth. Certainly, I would say, just sort of counting sort of the most basic ones. Obviously, Forth has a number of separate ones. This is sort of because the vocabulary of words that Forth requires encapsulates both sort of things that you would use nesting structure in Lisp to accomplish, but just also because there's sort of what's considered sort of part of the default set of things you have in a typical Forth is oftentimes a little more exhaustive in terms of what the machine can do. Whereas frequently, when folks are talking about Lisps, they'll carve it down to the absolute bare minimum set of operations that you might need. But at a broad level, they're sort of similar in that regard. The means of combination, obviously, in Lisp, there's nesting of those operations and nested expressions as a way to combine them, and in Forth we accomplish this with stacks, and that's primarily how we combine things. There's obviously a range of ways we combine things in Forth, but that's sort of the primary one. And then the means of abstraction. Well, in both languages you have a way to assign names to things, and that's sort of there's a similarity there as well. And then you build up from there, right? You have compound procedures, and for simple sort of pure functions, this works in a remarkably similar fashion. And similarly, as you start to compose things, the composition is similar. One thing that's sort of interesting, an interesting contrast, Lisp being prefix notation-ish. There's a lot of extraneous noise from the parentheses, the notorious parentheses, that is absent in an equivalent Forth program, but they're sort of a blessing and a hindrance as well, because you will end up using them as a visual guidepost. So I've encountered folks in my career who are they find it deeply tedious to read something like Forth's notation, but who are perfectly fine reading that deeply nested set of parentheses and prefix notation. Conditionals have a similar flavor, although where in Lisp they're accomplished by way of altering the order in which sort of normal evaluation occurs, and we'll dive into that in more detail later, such that you sort of control the flow of it. In Forth, the conditionals are mucking about with the machinery of how you compile. So that's sort of another similarity, but also contrast. And same kind of thing with other types of conditionals. They have similar kinds of expressive power. One interesting contrast is, of course, recursion is sort of goofy in Forth. We don't use it a ton, or we try to avoid it. It tends to have the flavor of complexity. It's squirreled away in this typically in recurse. One thing that Gforth does that I believe is relatively non-standard is you can state up front recursive, and then it sort of unsmudges all the things, and you call them by name. But either or, and again, quite similar. So one of the first examples they go through in the text that's of any substantial size is finding a square root. There's it's sort of this great example of decomposition of things, and breaks it apart into pieces to find an estimate and improve upon that estimate. It's using the old average and divide by 2 method of finding a square root, and you can express the same thing in Forth. Of course, this immediately bumps into one of the other fundamental contrasts about what is sort of basic, where in the Lisp version, of course, it's just assumed that floating point is a thing. In Forth, this is a little abnormal. A more normal way of doing this might be, here, let's do some integer math, that sort of thing. Then of course they dive into a recursive definition of factorial, and what they're really after is something like this, where they want to highlight that the depth of the expression evaluation relates to the sort of memory cost of the operation you're doing, and the same thing applies in Forth. The deeper you accumulate the stack, the more memory consumptive that particular style of evaluating something is. Notably, of course, the iterative version of factorial expresses does not have an intuitive syntax, but that's more because of the strong emphasis on it being not state mutating. So, and they of course then explore, the depth being shallow means that it's not consuming more memory. Bunch of similar examples is recursive Fibonacci, where the stack depth or recursion depth is exponential because you branch out at each point. But of course, you can re-express that one in an iterative form as well. And there's a series of early examples. And I went through the exercise of converting some of these just to kind of get dip my toe in the water in terms of thinking about, would there be some fundamental difference in how I would approach some of these very basic kinds of problems. Here's a one to count change in a certain amount, and there's a table of different types of coins. In a Forthy version of this, of course, some of the things that I would sort of intuitively here want to accumulate into a function end up just being plain data in a more Forthy style. but then, of course, we get to some of the interesting bits, right? One of the potent things about Lisp is that it offers higher order procedures, and namely procedures that manipulate procedures, and so the example that they go through is they suggest, okay, well, here's a function that sums a bunch of the integers from A to B, and of course, you can do this a number of different ways. And forth, you could do it with a recursive form as well, but you'd probably more intuitively do it in an iterative style. And then they say, oh, well, let's suppose you sum cubes, and notice how the summing of cubes is sort of similar in style to the summing of just the values. And the same is true with the fourth expression. You'll notice the sort of you're adding one additional thing. And then they say, well, what if we take this particular expansion of pi, or actually pi over 8, and notice how this too, you're summing some function of the of I at each position, but in this case you're skipping along by a step of 4, and so in the fourth version of this, you transition from loop to loop plus. And of course, what gets pointed out is, well, there's something the same between all three of these, and couldn't we factor that out into its own thing? And so what's proposed is to then use higher order functions and have a term function that is the thing that gets done on each term, and a next function for skipping along. And this allows you to then define sum of cubes or any of the other three simply by passing in some functions and an incrementer and the range. And you can do the same kind of thing in forth. It doesn't quite cut to the core of the issue, though, because here you're defining a function up front, and you're passing in the address of that function and using execute. So we'll get to the meat of that. Then, of course, what is really salient is lambdas and closures. And of course, what is the direct fourth equivalent? This is something I've pondered a little bit in the past, and I'm not sure I entirely have a satisfactory answer. Obviously, well, yeah, yes. This is indeed yes. This is indeed. I will. That is one of several possibilities I will enumerate.
The equivalent of lambda Lisp is no name in fourth.
Now,
Yes.
yes. So that as I explore here in further slides, there's a range of possibilities. One sort of classic canonical version of this would be to reference create does. Of course, this is fine as long as you're going to sort of name each of the things. One obvious thing is to make this dynamic, and there's this no name operation. There's actually two. So no name colon no name, I believe, is standard in some of the various standards. A fascinating variant on it that's present in G4 is no name without the colon, which causes any of the named anything that you've got a method to create. Sorry, I'm stating that awkwardly. It causes the next word that you create to be created without a header, and then you use lattice xt to pull out a result. The sort of subtle reason that I think that is a slightly closer approximation is that it gives you the flexibility of using the full power of create does to actually store some data in with the word, although while doing this in the middle of a definition, which this is actually a bad example of. You'll see some of this later as I use this in a variety of places. But there are other possibilities. There's a talk I gave, apparently in 2012, which is where I explored doing sort of general closures and in forth, and there I proposed a sort of a word set where you encapsulate something similar to no name that can be done inline in a function. But of course, then the problem is you have the issue of where do you put data, and so I proposed the notion of a scope stack that you can stuff things into. It will be embedded along with the definition and can then later be drawn from, so that you can accomplish something like that. To make that more obvious, right? You add something into the scope stack within this defined function that you've done in this scope. You can pull something out that was stashed away there and do something with it later. And a copy of that, the state of that stack, is made at that point. I'm not sure it's a particularly great way of doing, but it has a sort of a more direct equivalence to what you're accomplishing with a lambda. And there's a link there to the old implementation of how you can do that. And as is usual with Forth, you can often you have enough rope to do all the things, and so there's all kinds of different clever ways you can introduce this. There's also a paper by some of the, I think it's some of the Forth authors, where they explicitly try to do a literal lambda with local variable like syntax in it. And that's obviously quite complex and accomplishes the goal of re-implementing Lisp in another language, but is not particularly Forthy in my estimation. But your mileage may vary. So those are the nuggets that I plucked from chapter 1. Chapter 1, of course, a lot of it is about just introducing the student to Lisp, and so that's why the examples are kind of foundational in that way. So the things that I've plucked from chapter 2, this is about building abstractions with data. One thing I wanted to actually highlight is which is kind of, it actually shows up only in the text for whatever reason in chapter 2, and it touches actually on the prior topic, but is worth pointing out. They have a rather odd usage of the term closure in this text, and it's actually kind of highlights perhaps a sort of a historical contrast that where one has won out over the other. In the text, and they're very explicit about this, they refer to closure in a mathematical sense, in which they mean something very different from the way you usually hear a closure used, which is a function which captures its own environment. They use it to mean the idea of a set of data types and operations that where you can use all of them within the same group, and this is more close to APL, and it's sort of how everything is usable as an array, or there are other examples that we'll get to in a bit. But it's an interesting sort of a contrast, this idea of a set of operations and a set of data types that are where you sort of have completeness. The domain and range of all of the different functions that you're manipulating are the same. It's kind of interesting that they continued with this terminology for many years, even though the other usage, which ironically became popular because of Scheme to a degree, I think sort of won out in terms of how people typically use the phrase closure. So what they mean by, what this chapter primarily focuses on is sort of barriers of layered abstractions, where you compose layers and isolate them. One interesting thing about how the authors talk and think about this notion of barriers of abstraction is that it's actually surprisingly Forthy and has some resemblance to sort of the philosophy espoused in thinking Forth, in which, although you have layers that are isolated, they're not sort of hard boundaries in that OO sense. They're squishy boundaries in which you potentially can reach down several layers, and you don't try to rigidly encapsulate and make everything a perfect black box, but rather sort of find the appropriate level for everything at its natural level. And so the first example they run through is to build up a description of rational numbers, x over y, and they build it on top of cons, car, and cutter, and then build up making rational numbers as pairs using those, define a bunch of mathematical operations on top of those, and then describe the programs that use them. And although they do sort of highlight that you want the separation where there's a contract between the layers and you don't want one to know the other, they sort of do highlight that one of the sort of powerful things here is that you're not sort of closing off each level, but are able to think about each of them, if that makes any sense. So of course, now getting to the examples in this chapter, which start to build up things with lists, the question is how to do this in Forth. Number of possibilities: store them in the dictionary and leak like crazy. You can, if you wanted to use this in practice, I would say that you might do well to use a zone allocator, where you maybe bump the dictionary over somewhere else, fill out an area, for each of the different areas and then reclaim it that way. You could, if you desperately wanted to actually do a GC, you would have the problem that you're mixing sort of GC to non-GC things. If I had more time and deeper inclinations, I might have thought profoundly about what a garbage collected forth would look like. But barring that, you could do what I believe I did once upon a time in an earlier talk that I was not able to locate the source code for, but do a crude version of the BUM conservative collector in which the stacks or the memory space in forth are assumed to refer to if they have any numbers that look like they're pointing to something in the garbage collected area, then you conservatively treat that like a root as you collect. There are reasons why that can be good or bad, but when I hit upon an example of something where I feel desperate to use lists, then maybe that will be the point at which I worry about this. It's surprising how many even sort of toy Lisp implementations they'll just sort of punt on the garbage collector. So I don't know, but yeah. So here's what I did for at least a bunch of the examples that I worked through. I defined cons using this no-name construct, using create, and then stored a pair of values, and then get out the xt of it, so that you end up accumulating a little bit of data into the dictionary. Car, you simply execute that word, and then fetch out the cells, either the first or the second. Similarly, for an atom, I just use the dictionary to deal with deduping it, and this lets me define a name, and then I reference it by name afterwards. This isn't quite precisely like an atom in the sort of normal Lispy sense that I could have made a convenience word that fishes one out. And if you look back at what I did once upon a time for some literate programming and forth, I did do some deduping of that sort. But for these exercises, it felt like that was me building up a big abstraction on top of forth rather than sort of getting to the meat of the problem. And then just for convenience, the ability to print out those atoms and whatnot is useful. So there are a number of different examples in chapter 2, and I didn't want to work through all of them. And several of them are actually there's a mixture of things where they're done as sort of complete examples versus exercises to the reader. And I wanted to sort of hew to one of the ones that was not an exercise to the reader, so I could compare the Lisp side by side without sort of me saying, oh, here's the Lisp that I did to complete the exercise. So the generic operators one is nice because it goes through a bunch of these high-level abstraction examples, and it explores the power of the closure property in the first sense that I was talking about earlier. So basically, let me just run through this example quickly here. There's I've found that because I was using that definition I gave previously of pairs, I needed some way to stash up either a float or an integer in the same value. I made a very tedious assumption here, which is that I could fit both floats and integers in the same slot. Working on a 64-bit forth, I was able to get away with that. And then there are a bunch of places where scoping is used very heavily to isolate things, and so I came up with some word list manipulation to isolate definitions away and namespace them. And then surprising number of the examples involve squares, so you need squares. A data structure that's used throughout this generic operators example is a big table, and there's various places where they actually give a fairly roundabout definition of such a table in the text, and I think there are parts of it that they leave as exercises to the reader. But basically, it's just a table where you can store an operation, a type, and then an item. So it's sort of two keys into a dictionary. And so rather than have this, and they use multiple of these for cases where there are you're building up tables that are unrelated. But in almost every case where they use it, one sort of immediate simplification and sort of fourthy thing that occurred to me was, well, there's no cases in which the operations and the types overlap, so why not use a single table for each of these things and have it be a single global thing? So here's my table. This got snuck in there, but basically it's wrapping a cons around an item to distinguish between its type tag and its contents, and then building up a table that you can store items in and get the equivalent out. And this is, you know, stored in just in a gigantic list of pairs. So then in the Lisp version of things, they go through and have this apply generic. And I should back up. I just realized this the example doesn't sound very motivated if you're not realizing what I mean by generic operators. So the example that they're running through is they're trying to provide a generic set of plus, multiply, times, and divide that work on rational numbers, that work on complex numbers, that work on polynomials, that work on regular numbers, and sort of carry that through and see what the implications are. So, so they have this generic application function that takes an operator and then a bunch of arguments and applies it to something that you looked up out of that table. So what this table is accomplishing for you is it's your object-oriented lookup. It's given a type and given a value. You look up its type. You see what function you're going to dispatch it to. So it's a giant V table that's shared between multiple operations. They have a more extensive version of this. One of the reasons I skipped over doing the equivalent, I'm really only doing the parts in fourth that are in bold here. They handle type coercions, and so they have a second layer in which, if you imagine an operation like addition, if you're combining a complex number with a non-complex number, maybe you need to do a type coercion to get them in the same type before you can do anything. They leave chunks of this as an exercise to the reader, so I decided to avoid it for fourth. Here's what I end up doing for fourth: just going into fishing out the type tag, fetching something from the table, and then getting out the contents of the item and applying it. And there's one version for single argument functions and one or for single argument words and one for double argument words. So then what they do in this, for example, they build upon it complex numbers here, building both from real and imaginary, but they also do a polar, they do both polar and non-polar complex numbers. And you can do something similar. So I'll declare all my atoms up front, so I get those names reserved in the dictionary, and then I have this generic, function that will pull out the real part of a number or the imaginary part of a number, pull out the magnitude, pull out the angle, and then functions that can convert. And so you'll notice this is all just, it's generic. There's no I haven't defined yet how you do any of these things. I've just defined an interface. This is very similar to this, right? You're defining these generic operations and you haven't yet said what they're going to be. And then you can actually go and define how you're going to do complex math on top of these. And the reason they've used both polar and rectangular is this nice property where it's a little bit easier in the polar form to do a multiply and a divide, and it's a little bit easier in the rectangular form to do plus and minus. And so they use the two to sort of justify defining one in each. And you can do the same thing in fourth and build up complex math this way. And I've got some words to print for convenience. They then build on top of this they then in an isolated scope install all of this into install those definitions for complex math into the generic definition for rectangular, and I can do the same thing in fourth, and then the same thing for the polar form and similarly. So before I move on to the next section, actually no, let's go through these and then. So then the hierarchy you've got here, if you can imagine, and I'm realizing I'm missing a useful slide here to be able to do not want to draw on the whiteboard with a Sharpie. That would be bad. There we go. So just to be clear where we're at, you've got complex numbers and you've got rectangular form and you support those, and you've got a polar form and you support those. And then you can say, okay, now I want to describe generic operations for addition, subtraction, and multiplication. And I want to be able to represent a bunch of other kinds of forms. I want to just plain numbers, scheme numbers, and in the case of the list version, rational numbers, two types of complex numbers, and polynomials. And I can do the same thing. And in my case, I've given them sort of nice little pithy fourth names. And have each of these, again, be these sort of generic versions that go reference this table. And just as they can go in and add in scheme numbers, I can go in and put into the table basic operations using simple numbers. Of course, these are simple numbers in the sense that they're integers, which is different. So I also go ahead and put in floats and keep floats in there as well. They go in and install the complex numbers all as one unit. So now if you're, again, following along here, you've got, you've got your add, sub, etc. They're supporting complex numbers. They're supporting simple numbers. And in our case, actually, it's simple. It's really ints and floats. And then, and similarly, you can bucket barrel them in. So, and in each of these, you're declaring the operations. You're attaching a type tag to them so that you can tell what kind of number it is, and then putting them into the table. They then go ahead and install rational numbers, and they actually define rational numbers in line. There's a prior example, actually, that for reasons that don't make sense, they don't reuse that one. So it's 2 pages long, and I likewise do the same thing. So then you can stick rational numbers in, and so far this is sort of cute, right? You've got sort of your OO definition of a number. I can do various operations on it, and it dispatches to the right version. But then the one that's sort of fascinating and feels sort of unusually potent is that you install polynomials. And so you have a definition of polynomials where you define them as, what variable is the polynomial in. You have a list of terms of the polynomial consisting of what the exponent is. You assume it's an integer, and then the coefficient. And the sort of key magic thing when you actually get down to the definition of adding and subtracting them is that you see this G plus here, or similarly, if I can find it in their gigantic, this add, you use the generic operations when you manipulate the coefficients. And so now it becomes a closed system. So you have polynomials, which are one type of generic type of data that you can operate on, whose coefficients are in turn generic types of data. And so that's sort of where you get that closure property. And similarly, you can do multiplication. And so then what this gives you then, of course, right, is that you have polynomials that are composed of ints and floats and so on, which is a kind of a neat recursive thing. And so let me just quickly give you an example of how this works. If you let's see. So for example, so I have these rational numbers, and you can print them. They're generic. You can have you can add them, but more importantly, you can manipulate them in all sorts of interesting ways. Let's say I do half and oops, third, and then let's suppose that I do a let's say I do half to the second. Oops. Let's see. Oh, I need to do. Say I use x, And I've still got something off here. Oh, those are not printing. So I can define I can define 1/2 x squared, and perhaps I could do, let's say I do x third to the 0th, and now I can add those two things and print them. So I can have 1/2 x squared plus x to the 0, 1/3 x to the 0. I could maybe define that as w, and I can have w and multiply it by itself, and then have it do the polynomial math, but with the rational coefficients. So that's that. All right. So how are we doing on time? Let's see. I shall endeavor to go along. So the next example is a little more visual. There's this picture language that's described in the text, and it actually comes from there's a paper on someone trying to sort of reverse engineer one of Escher's pictures that was done way back in the 80s. And he devises a high-level language for describing pictures and building more complex pictures out of smaller ones. And it focuses us on recursive and symmetric images. So the sort of goal state is this particular painting called Square Limit by Escher. And what it does is it uses as a basic building block these coordinate spaces where you define a horizontal and a vertical axis, and then some offset to those. And then take a building block like this and put it into a pattern like that and get something like that out of it. So to be able to do the same, I emit some PostScript to draw a line and to show a page. And then just as they define a set of functions to manipulate transformations, I do the appropriate thing in Forth and define a transformation stack and provide a way to push transformations on and off of that stack. This, of course, then lets me define or apply a transformation to a set of coordinates and to draw a transformed line. Throughout, by the way, I'm using integer math, not floating point math. And then I can define a bunch of basic transformations by manipulating the items on that transformation stack. So scaling and diagonal flipping and turning, and I use a slightly different definition for atoms and cons here. Oh, sorry, no, this is the same definition. That's mysterious. And then as they build up operations like beside, to say I want this picture beside this other picture, I'm likewise able to build up a definition of beside using my transformation stack and specifying a scaling factor for the thing on the left, the thing on the right, similarly placing images above and below each other. Or doing that with some scaling factor, in this case, a third, which is a magic number for this particular painting. They define a vertical flip operation, taking an image and flipping it vertically or rotating it 90 degrees, and I can do likewise. They also, and I should confess here, I mirrored some of what was in the text, but they actually leave some of they do some of the steps differently in the text than in the original paper. And I went back to the original paper because in the text they, and I don't have a slide of it, they do this particular operation where they've got these Taft squares, and they do a 45-degree kind of a rotation. It's not exactly a rotation. And in the example in the text, they actually do it without the rotation. And so it has the similar kind of exponential squishing pattern, but they don't have the rotations mixed in. And I thought, well, let me mix in the rotations. It's not that much more difficult. And so I have this turn 45-degree operation. Oops. And then similarly this rot 45-degree. And then I define my basic fish. Of course, in my case, I did this for the fish because I didn't feel like drawing a fish, and this was simple enough to draw. So, and then I use this is verbatim from the paper. They have this definition of fish 2 and fish 3. So this is that are these sort of composite units that they build the picture up from. And then they define the notion of a quartet, a unit of 4 items that repeat in some cycle and a corner. And this is, again, all just a very literal transcription of the functional description in the paper. And then they describe a no-net. I don't know why they use that phrase. It's just a 3x3 grid. And then the actual square limit is defined in terms of that. And the interesting thing is it's parameterized. So you can choose how many layers of recursive depth you want to it. The actual painting uses three layers. And so you can run it likewise. It's worth pointing out that each of these, in fact, I should back up and look at a simpler one here. Throughout, I've done these in such a way, actually, this is a better example, where the beside operation, actually, let me go back to beside. The beside operation does a cons and then a does that stacks on that cons, so that what you're getting out of beside, you take in a function a and b that define the 2 sides of the picture, and you get out a definition, the xt of a definition that is the combination of those two beside each other. And so you're not merely taking in data, you're taking in a function and then returning a function at each point. And then inside of that, executing each. So this lets you do square limit 3 and get something like that. All right, chapter 3. I did not dig in here. This is about register machines. In some ways, actually, this might be an interesting one to look at in the future. Part of why I skipped over this one is that a big chunk of the book up until that point is look at all the wonderful things you can do without mutable state. And then here, let's look at mutable state, how horrible it is, but also the interesting things you can do with it. Mutable state is, of course, not sort of verboten in that way and forth, and so there's not as much sort of it's sort of hashing over things that are typical in forth usage. There are some interesting things in the chapter, like a simulator of electrical circuits, which might be interesting to see side by side. Or similarly, what generators and infinite streams look like in forth might be interesting to explore. And there is a little bit in which they touch on concurrency, but it's in a fairly simplistic way, and so might be worth revisiting in the future. Chapter 4, this is, of course, the big one for Lisp. The big selling point for Lisp is its sort of meta-circular evaluator, and the fact that it's a very simple language to define in itself. And of course, this is also where you get one of the more interesting contrasts with forth, right? What does a Lisp and Lisp look like versus a forth and forth? A thing that I did not in my CS curriculums use this particular text, but it was certainly the case that folks love to trot out these wonderfully pithy, 1 or 2 page descriptions of Lisp and Lisp. Forth, we sort of do this and we sort of don't, right? We tend to be a little bit more realistic in how when we describe forth from the ground up, we tend to actually describe it oftentimes in terms of a machine code description of how you would actually emit code. We rarely do the sort of not exactly cheat, but the sort of intellectual simplification that you get with a circular definition of Lisp, in which you reuse the parser, you reuse a lot of the machinery of whatever machine underneath you're building your Lisp on. And so when you see these sort of Lisps and Lisp, what they're oftentimes doing is they were saying, well, it's not interesting to talk about how we do addition and subtraction. It's not interesting to talk about how we do parsing. Let's assume we've got these things already there as Lisp data structures, and then I will just describe how function application and evaluation work. And so I thought it would be interesting in doing this comparison to try to do something sort of similar with forth. And so, right, the idea with these metacircular evaluators in Lisp is that you can basically have these 2 functions, eval and apply, and eval sort of is the core of the evaluation rules for Lisp, and apply does function application, and that is sort of a closed complete set. In the version that's in this text, I actually there's another textbook by a fellow named Jan van Epschoot that I used in school that actually literally has like a 2-page description of Lisp that's sort of closed. Of course, it doesn't do a scheme like Lisp. It actually uses environments that don't have lexical scope. So that I think helps make it a little bit simpler. It's easier to do that way. This one ends up relying upon it's more readable in some ways because it's actually factored. The one in the text I'm describing fits on 2 pages because it's just one ginormous pile of stuff. The one in this text breaks the problem apart into, well, how do I evaluate variables? How do I evaluate coded expressions, assignments, definitions, and then the conditionals and all of these. But of course, then the key thing is that when you get to the point of deciding you're going to apply a function, you call eval you call apply on the eval of the operator and on the eval of the operands. And then apply, in turn, does this step of evaluating the bodies of the procedures, and that's how you get sort of the engine of Lisp to go. In Forth, of course, we can sort of do something like a meta compiler, and what I've tried to do here in this one, as I went through, was to keep it simple and small, and sort of use the same cheats, as it were, that your typical metacircular Lisp is using. And so step one, I just say, okay, I'm going to just go ahead and define an R stack just directly. I'm going to define an instruction pointer and a working state, a work variable to let me do sort of a conventional threaded forth. And then just as in Lisp, they sort of separate out all of these pieces to evaluate different types of expressions, and actually quite a lot of them, and to look up individual variables. I will describe sort of a minimal dictionary. And the thing here is that I end up in this definition of a dictionary. I used something. I avoided. One other thing I did as a simplification was avoided using. I avoided using multiple different size widths. So everything is cell sized, and then I build up the dictionary. But you'll notice that I reuse parsing completely from the host interpreter. So this all comes up in gforth, reuses the gforth parser. But then re-implements a second dictionary on top of it, link access and immediate words, and then has these words p colon and p arrow to bucket bell primitive words from the host forth into the target forth, and this is not actually a direct correlation, but just as there's dedicated code for evaluating ifs, of course, then you get the core interpreter words for create and does and do colon and branching and such, and then you can this is also oddly out of place, but anyways, you can build these up in the host environment, and so then one other thing I do still in the host environment is build up find. So find is done sort of directly still in the host environment as is words, just because that made my life easier to debug. And then a few keywords get sort of bucket belled over, implementation of literals, exit and execute, and then colon and semicolon. And then just as in this sort of simplified version of a Lisp interpreter, they pull in all of the primitives, I'm able to then bucket bell over all of the simple primitives. And so for a bunch of them, they are just literally passed through. I'm anything that's with the data stack, I'm just bringing over verbatim. I bring over all the parsing words because those are sort of not cheating in the same sense that they don't assume anything about the world. And that's actually a huge simplification I've found in the past. Whenever I do sort of do forths, I spend a lot of time sort of thrashing around, worried about how to bootstrap the world and think about parsing and sort of tie myself in knots over it. And this was actually kind of clarifying. And then there's a very small number that are re-implemented. And this is really the core of what's happening in the. You could say this is sort of the metacircular set in the same sense. And then just as they declare a prompt and do all of that, there's a little bit of GARP here to provide a normal sort of OK prompt and errors and all of that sort of thing. And I called it circle fourth because, you know, metacircular and all of that. And then I bootstrap, and then I have a whole bunch of stuff that's in compound words. And so there's this core that's really just this list, and then of words, and then the rest are all defined in sort of ordinary high level fourth on top of that. And so you get, you know, things like this for most of the words, things to manipulate the compilation state, a little bit of a few items around quoting, and then, you know, typical flow control built on top of branch and all of that. Compound words like min and max, and then postpone works in this way, and counted loops and so on. Exceptions, although I didn't. The one thing I'm a little unhappy with is that exceptions don't actually sit underneath the main eval loops. If you get an error, you just get an abort actually up at the top level. You don't get a real exception, which is one place where the loop doesn't close. But it's nice to actually be able to do constant and variable in terms of create does. And then I just while we were sitting here, I added C just because I wanted to actually be able to demo that. So in total, it's 84 lines for the core for bootstrapping and 85 lines for the compound. So it's like all the code was just up here on the screen. Let me give you a brief demo of that. And so, you know, it's a fairly small little fourth on top of G fourth, and, you know, can do sort of all the usual whatnot. That, and because I implemented C, you can do things like that, and you can do C. Let's do constant, and you can even see those because they're in high level definitions. And so so again, you know, that's it in terms of the core, and then the compound ones are really quite pithy. It's an interesting exercise. I'm not sure, like, because it relies upon pulling in all the primitives from the host system. It sort of feels fake, I guess, compared to your typical bootstrapping a fourth. But it's an interesting contrast that you get something that's relatively pithy. One thing that it did make me wonder overall is, of course, the very pithiest definitions of Lisp are frequently extremely small, and it's because there's sort of this agreed upon set of like what are the most basic operations in Lisp. With fourth, it gets squishy because, you know, do you need to have create does? Do you need to have you know, the full set of operations, or do you have sort of the minimal set that are marginally Turing complete? And it's an interesting thing, I think, in terms of sort of evangelizing the simplicity of fourth, that I think we don't have that small agreed upon set of what the core is, which I think is fascinating. I largely skipped chapter 5. This would be another fascinating one to revisit. This is primarily about compilation to a register machine. In some sense, the Lisp that they bootstrap in this chapter is actually very similar to all the extra complexity that's typically left out of these metacircular samples, because then they now have to worry about actually what are you actually doing to build up the garbage collection, what are you doing to actually build up instruction generation for some target machine. It might be worth exploring also, this might be a good place to explore a sort of fourth in which garbage collection is sort of core to the implementation of it, which might be fascinating, or some smarter terser version of fourth compilation, but a thing for a future talk. So notable learnings, lists and fourth can be kind of handy. It was kind of neat to be able to see the polynomials and complex numbers and whatnot work quite that way, although I'm not sure that was sort of worth the fact that it's leaky and a little bit overly complex. I like this idea of closure in the math sense, and it sort of reminded me of what's fascinating about things like APL and some of these other similarly sort of closed mathematical groups of things with the domain and the range of the operations is the same, something I feel like I might want to visit in the future. I think it highlighted to me how much having a tighter core to what we consider fourth might be helpful in evangelizing its simplicity, and might help tell a clearer story. And also, it made me go and look at a bunch of Escher paintings, which are kind of nice, and reminded me how nice those are. Mm-hmm. Indeed. Also appropriate for the metacircular whatnot. Questions? Sorry if that went a little fast. That was actually way more slides than I should have had. This is what happens when you say, oh, I'm going to take this ginormous book and I'm going to go through and convert a bunch of the examples, and then you realize you have a bunch of examples and not the content of a talk. So thank you all.
No, hurry. It is break.
Before you at 2:30, right?
Yeah, you go before me.
At least you're using bracket, but then you went back to that. Yeah. Why did you do that? Why did you bracket? Why did you bracket? Because some of my other stuff was old packages. So I want to hear it. So like just being able to sort of like was like seeing that. Yeah. But anyway, that's why having it so that's so because I was thinking like I don't know if you want to write similarity currency or something like that. Yeah, it is. I wasn't going to do the whole story, right? But read stuff, yeah. But then I don't know. Yeah. So I just have a separate goes for channels. One of the other that makes sense. I have a lot of great to go, but like the way strategy yeah, except they go together. Once they do, they ran out of stuff. They still have shit. They're making new boards. I've been making I thought they were like gone. I thought they were like directly with dead, but like it's no numbers were websites. You went to color court? It's nice in the sense that that's probably I didn't know. I'm like, it might be a second. I don't do that because like that's like I want to go to anyway. So I want to go to green engineering, and I basically get to do this all the time. So I don't like. Wait, what? That's cool. Has
Is actually done. I think the last others are the building blocks are by numbers that concepts and everything's still that atoms for the project. Built a concept they ran out of boards. The boards really I think on the app too was that decided to make it all.
That's
Sorry, there's no blue light filter on this talk. There's no blue light filter on this talk. I'm going to sleep tonight.
So what else is new? Yeah, I get too much, way too much blue light anyway.
Yeah, we could always do with a little less blue light in our lives.
It depends. See, and I don't see red light. Blue is the nice one. I can see blue.
My father is colorblind and he likes blue as his favorite color.
Yeah, I am too. Yeah, blue is my favorite. I can see that one.
Yeah.
Red and green.
I don't like asking right now.
Yeah, I think
Are we doing it now?
10 minutes.
Cool, because I need to do something right.
that's two single things.
Part of me just wants me to just throw the raw source file up on the screen and just can read from that.
Yeah, here. You can all read this.
Yeah. Here, I'll just scroll.
Some parts of my talk I put a little too much source code just directly in there.
Oh, I'm talking about the script.
Oh, yours? Yeah.
Like a whole script.
You will be singing the Benihana birthday song, which was instituted because they didn't want to pay copyright on the birthday to the bird function. Bird is a word that drops in the stack, turns back.
Officially, it's in poetry.
Definition. They tend to about like how once in a while they hear something they made a final ruling.
That's my problem. I'm not sure I could understand it anymore.
No, yeah, it's unfortunate.
The problem with this system is that tools are very the same.
Damage. They'll just say, okay, we're going to let you do it for $1 to show. Yeah. There was a problem at the time. There were 2 kinds of. You always have the answer. There's 2 guys. They don't get along. And so they ship their stuff separately. These 2 have it. They don't have to touch it. Other problems. I don't know what I do. I figured out. That is my enthusiasm for
All the way to the top.
Hello. Now you hear me.
There you go.
One of my favorite parts is the conversation it breaks. And now it's over. I'm so sad.
Figure out.
Ken, you stop listening too. John, stop fucking. Class.
Dismissed.
It's one of the very classic comedy routines that.
Yes. That's the first punchline. Cheech and Chong's trip.
As they be.
It is.
Available on YouTube video now.
What?
Are you plugged in?
Am I plugged in?
Oh, you are.
He is plugged in. He's ready. We're alive.
I'm wired.
Engage!
Sort of.
Okay. So I'm Andreas Wagner, and I am revisiting Gelforth, which I haven't worked on for quite a while. I think I gave a talk on it at 4th Day 2016, and it actually is working now. The routing fabric, it actually works. It's not fully built out yet, but it's mostly working, and there are some things I'm doing differently this time for this fourth HDL for the PSOC 5LP. Actually, let me back up a moment for those who haven't seen the first one. The PSOC 5LP is a chip it's a Cypress chip with a ARM Cortex M3. It has a CPLD FPGA fabric called the UDB array, the Universal Digital Block Array, and that's sandwiched between the UAB array, which is an FPAA, which is a field programmable analog array. They call it the UAB array, the Universal Analog Block Array. It's basically equivalent to the Anodyne FPAA, but it's integrated with everything else. So you can, it's all memory mapped. You can access everything from ARM, from the ARM Cortex M3. It's all mapped into memory. The entire routing, digital logic fabric and routing fabric and FPAA. So I'm writing a fourth HDL for that. And the idea is to compile high-level fourth code to the UDB array, later also the UAB array. And in 2016, I was I was basically implementing logic gates like XOR, XNOR, so on and so forth, with a fourth Boolean algebra like word set. And I didn't really like the aesthetics of that. So this time I am using this fourth HDL implicitly as it's sort of implicit in the control flow of the fourth program. So you have a sequence of words that's sort of like an AND series circuit, and you have a nesting of words, sort of like an OR logic, like a parallel OR logic. And this has the advantage of blending together with ARM machine code words easily. You can mix and match the two in the same source listing, sort of same source code. It's all interactive anyway. And I saw Sam Falva's declarative, inquisitive, then imperative paradigm. I think like even before I moved here. And the way I understand it is that it's basically you have a sequence of truthful assertions in pseudo-English, at least the declarative part of the paradigm. You have a sequence of pseudo-English truthful assertions, and it executes those assertions. And it's true if it's executing something, it's a truthful assertion. If the program could not continue without being untruthful, you exit to a higher level, and the higher level of fourth code is more vague, and that's then it can still read true because it's more vague. It's more of an abstract description of that's more of an abstract assertion. And yeah, so the control flow is any combination of these ands or ors in various ways, which forms sort of Boolean algebra in a way. I think there's a Boolean algebra hiding in the control flow. And but this is how it looks currently. I just pulled this out of a test that I had in my source code for my place and route tool, place and route library. I wipe the logic fabric. I turn off the disable the UDB banks. I set these two GPIOs, 6.0 and 6.1, to high, and then I outputs to the GPIO 2.1, which is connected to the blue LED on the board, on the breakout board. Then I enable the banks, and then it works. This creates an OR gate. This is how it looks right now. It's not quite the control flow thing, but it's getting there. And how do I do this? I use the hyperstatic scoping in the dictionary, like Ting was leveraging the dictionary earlier today to, rather than writing like a separate database application or something, he was leveraging the dictionary that's already there. I sort of did the same thing. I leveraged the hyperstatic scoping of the dictionary to shadow inaccessible routes with redefinitions of switches in the word set. And to expose accessible routes, I give them unique names which are visible from the perspective of some other switch. And this is relocatable throughout the source code, and from the perspective of a switch, you can see it sees through redefinitions and unique names. It can only see switches that are, it can only find switches in the dictionary that are accessible and not already configured for some other application. And so I connected switches get redefined with the same name. Exposed switches get unique names. This is something I should automate with the union find algorithm or similar, maybe quick find or something, topological sort. But currently I'm doing it by hand to get a better understanding of it. So I have this, so when I was doing this by hand, I have this small footprint of code for switches that are exposed. And I find that I'm like copy pasting the same excerpt, same snippet of code, many places, many different places throughout the library. And it's like extremely redundant. It's exactly the same code, copy pasted to different locations with no modification to it. So that's cool, but it takes a lot of space in the Flash or the SRAM dictionary. So yeah, so actually here I have a small of the cut out, screenshotted, and you can see you have the switches, and they have the same edge layout pattern to these edges, the connections, but they're convolved in different, they're convolved with each other. So that gives you an idea of how that would look in the fourth source code. And to eliminate some of the waste of space from copy pasting the source code, I use Mark Smith's bind word as a trick to relieve that problem. And so it has a body field after the link field, which points to the body of the word. This allows you to fetch the scope of a word and use it somewhere else in some other word. And this helps avoid placing the same exact source code at different locations in the place and route library. So yeah, I can use user-defined logic. The user can insert their designs into the fabric and then have a single word to load or embed words that load other parts of the fabric description. And this could be temporary words that get thrown away when you don't need them anymore, like temporary compiling words. And previously in like 2016, I was trying to find I always thought I had my finger on a idea for a formula that captures all of the routing fabric with a simple formula, but I never got quite there. It was always just on the tip of my finger. I was just about had it, but never quite. So I think this is more pragmatic to use this hyperstatic scoped place and route because it works with heterogeneous fabric. It will work with the data path. It will work with various oddball hard IPs embedded in the fabric. It will work with user configuration, user-defined routes, soft logic, not just the hard accessible routes that could be configured, but also what the user has configured already, because that blocks other routes. And yeah, the PSOC, as I said, the PSOC 5LP fabric is all memory mapped. So I was thinking I would keep the logic in there only as long as it's needed, and then reuse the space for something else. Just sort of keep it very dynamic and sort of like register allocation. I don't always keep the same thing in registers for the duration of the entire program, because that'd be kind of a waste often. And yeah, so you can do all kinds of things with this. You could do just-in-time logic synthesis. You could do lazy evaluation. You could do super compilation, which is a technique where you have sort of a generalized partial evaluation where you evaluate various paths of the program before it actually needs to be executed. You sort of pre-execute the program of it. It's a more general version of that, super compilation. And so timing characterization. I saw in Chuck Moore wrote an article in one of the formal proceedings where he had this really nice, nifty, concise EDA tool, like it's for timing analysis, timing characterization of circuits, and you can have some delays for like some basic primitives, and then you can build more complex designs, and then it will spit out the delay of the how long it took to like the timing characterization of your design. So I have my repeated footprint, which is of exposed routes. So I just can characterize that. I use that as my primitives, and then I can I can get a timing analysis for my configuration using code from Chuck Moore. I just had to fix a few transcription errors that there's a 3 and a 2 that got transposed in this listing typo, and there shouldn't be a colon there before the rotate, but otherwise it works out of the box from the old source listing. And here it is corrected and with a few something factored out for the status and time. I just factored that out for clarity. And yeah, so if you're interested in learning more about how the PSOC logic fabric actually works, I have this project where I put a documentation up and I reverse engineer the routing fabric. And I also have some example configurations so you can get a feel for how to implement it at a low level, but eventually you won't need any of that. It will be just high level fourth, but the example configurations give you an idea for how to do it by hand actually. And if you're interested, maybe you should consider following the project on hackaday.io. I would appreciate it, and you can keep up to date with it if you're interested. And thank you. Any questions, comments, worldviews? So,
foresee this also working with the analog fabric as well as with the digital fabric?
I hope so. That's my goal, at least. I don't know much about the analog fabric. I know that it's pretty similar to the Anodyne design. It's actually very close to it. So the Anodyne documentation is more open than the Cypress documentation. So I was gonna read the Anodyne documentation and see what that tells me about the Cypress FPAA, because I think it will tell me a lot. But they made the UDB array and the UAB array such that they can work well together. So I think this will work for the analog array as well. I think it will, because this works with a very heterogeneous logic fabric. Although the UDB array is it's a very clean and elegant design. This is from a time when they didn't just do some automated thing and then get a hairball out. It's when they actually put a lot of thought into this design, and they did a really clean job on the design of this logic fabric. And it's pretty nice actually to work with. Yeah. Anyone else? All right. Thank you. They turned off for now. Oh, Sam Falva's coming up. Sorry. All right. Give you the mic in a moment. Yeah, the mic, yeah. It's on.
Here we go. Hi, I'm Sam Falvo. I am going to be talking to you about a topic which I haven't revised or haven't really revisited in quite a long time, going back almost a decade, actually a little bit more now. I'm actually just going to be reading from my script because my current day gig requires that I work many 12-hour days, and as you can imagine, I don't really have a whole lot of time to prepare slides anymore. So, what is aesthetic programming? Well, it has its origins as far back in 2008 when I first did a YouTube video, which, thanks to Andreas, is preserved now is now preserved on YouTube, I should say, where I used Forth to implement a text processing engine, basically a macro expander, if you will. Someone on Reddit had discovered this and was like, bah, Forth is unsuitable for text processing. Unsuitable, right? So in 2009, after I'd caught wind of this, I decided to use that same text processing engine that I wrote in 2008 to come up with my own blog engine, which I named Unsuitable. And as I'm doing this, of course, I'm learning, how to. I'm still evolving my Forth programming style at this point. But unsuitable was notable because it stored the blog it stored the blog articles in block storage, not in files. So it was unique in that respect. And then I figured, okay, well, I've got this cool blog. What am I going to do with it? So part of one of my interests is long distance optical communications. So I decided to form Project Dot, which to this day remains unfinished. And that was in 2010. But the development work that went into Project Dot was actually very instrumental to creating the declarative, inquisitive, then imperative programming technique, as well as the aesthetic programming technique, and so on and so forth. It's actually a family. It's actually a member of a family of 6 programming techniques. A lot of people think DITI, or DITI as I like to call it. Assertive programming has also been called. They think that that is like the thing, and it's actually not. It's actually part of a system of 6 different programming techniques that all mutually support each other. I won't go into those 6 today, but I will talk about aesthetic programming, which is the second member of that family. So aesthetic programming, what is it? It's characterized by or suggesting the practice of severe self-discipline and abstention from all forms of indulgence. Now, on the topic of self-discipline, so here's where I'm going to start reading from my script because I'm thoroughly unimaginative. On the topic of self-discipline, fourth programming always involves a ton of self-discipline. You have nothing really to support you. How many times have you been in the middle of an intense development session only to have your dictionary get thoroughly corrupted? I did just today, actually, which I will show you a little bit later on, maybe. But this happens with disturbing regularity for me, even in an environment such as G4, which is arguably one of the most memory protected environments that exists in the fourth community. Right? So it's not a matter of how the dictionary got corrupted, but rather it's a matter of why you let it happen in the first place. Right? That is the philosophy of fourth. Right? It's incredibly libertarian as programming languages go. So fourth is just following orders, right? So ensuring that this never happens has always been your responsibility and yours alone, right? So the second thing I'd like to point out is about the definition is the focus on indulgences, right? So we've got the self-discipline part. Now we're going to look at what an indulgence is. So earlier I'd mentioned memory protection. It's a nice feature to have. You know, it really helps you catch a lot of bugs, but it can also be over-relied upon as well, right? So what is memory protection? Well, it's a great tool when developing software because it can help catch programmer errors entirely in hardware. It's also useful for sandboxing untrusted software, right? So if you grab code from the internet, you know, let's say I start suspecting that Andreas's computer has been infected with a virus or whatever, and now I'm like, you know what? His code's been acting a little bit strangely. Let me run it in a protected environment, right? So memory protection actually helps out greatly there. And this is actually why operating systems have both kernel space and user space, right? It's actually a very primitive form of memory protection. So a feature like this becomes an indulgence when it ceases to be just a useful tool at your disposal, or something that you can swap out at a later time, right? So if your software depends on memory mapped files, for instance, well, this is a feature that both Windows NT and Linux provides, as well as BSDs and such, but not all computers actually have memory mapped files, right? So if your software depends heavily on memory mapped files, that becomes an indulgence. Like the fact that you cannot just swap that feature out, okay, with a moderate amount of work, That basically means that you're relying on that infrastructure. This is not necessarily a bad thing, by the way. I'm not saying that this is to be shunned at all costs, but it is something to be aware of, right? It's an indulgence. So one of the more famous features of Forth is that it has an absolute lack of syntax. And this isn't entirely true, of course. Some syntax must exist because you need to be able to control the interpreter and the compiler and so forth. But it just happens that the syntax is defined in terms of the language itself. And Forth is unique in that it has the smallest Cartesian product of syntax and semantics necessary to write useful software. However, that doesn't mean that Forth is convenient to use for some kinds of programs. In fact, as any contemporary programmer would readily note, it's quite a bit more convenient to express algorithms in languages that have richer syntaxes and semantics than Forth does. C++, for example, has a fantastic mechanism for managing dynamically allocated resources called RAII. Resource acquisition is initialization. That's what it stands for. And it's a pattern, it's a programming pattern, just like aesthetic programming and just like Diddy. But it's impossible to implement without necessary language support. So if you write your software that depends heavily on RAII, that is also an indulgence, right? So we basically have two types of indulgence. We've got the runtime indulgence, where you're relying on external services, and then you have language provided indulgences as well. Aesthetic programming does not say that you should avoid language specific features or environment specific features. I suppose I should change that. But it does not dissuade you from using runtime tools in a responsible manner. What aesthetic programming does, I hope, is establish a way of building software that minimizes dependencies. And you'll see this word coming up frequently. Minimizing dependencies upon these indulgences, thus promoting portability and maintainability. Right? So aesthetic programming, to put it in a nutshell, is a way of writing software that can be easily compartmentalized and actually packaged, if you will, so that you could write software that runs in more environments than you typically would otherwise. So aesthetic programming involves writing modular, extensible, easy to maintain software that avoids the use of clever language semantics or its notation. So in other words, not saying that you have to avoid RAII at all costs, but maybe there's a better way of writing software so that you don't have to rely quite so heavily on that semantic. So note that it covers all the indulgences discussed earlier, right? So people who have seen this presentation before might even recognize that I've since adjusted this definition to be more general than it was before, because previously I used to single out object-oriented programming very specifically. That is no longer the case. Because what wasn't stated in my previous talks was the implied assumption that you are actively programming in Forth. And what I was trying to argue back then was that object-oriented programming in Forth was a very unnatural style of programming, for me at least. It certainly seemed that way because you had a lot of dependencies. You had the dependency on the object-oriented paradigm itself. You had the dependency on the tools that you were using. And if you wanted to integrate one module with another that happened to use two different object-oriented libraries, you had your choice of integrating both of those libraries together, or you had to rewrite one in terms of the other, and so on and so forth, right? So basically it ended up making code integration very complicated. So I'm going to move on here. So basically, we do away with objects. With aesthetic programming, we dispense with the object orientation as your go-to abstraction of choice. This isn't to suggest that you would never use object orientation. I was very clear to state this in the previous talks, but it seems to get lost in the noise. But it should be treated as an abstraction mechanism of last resort. Depending on the abstraction level of your programming language, you'll find that this nicely, if somewhat inconveniently, solves some answers to perennial problems in programming. Who owns your object's memory, for instance? Is it you or is it your library? Very frequently, you have to double check. And garbage collected environments are not immune to this either. Right? So who's responsible for disposing of your objects? Right? Garbage collection helps, but it is hardly a cure-all, especially when you're dealing with non-memory related resources. So we also do away with message passing. I'm probably going to gloss over this a little bit because I don't know how much time this will take to read fully through. But basically, in object-oriented programming, you have the concept of message passing. And this is not something that many people frequently realize. When I say x.foo, and pass it some parameters, people think, oh, well, I'm calling a method. And that's true, you are calling a method. But the actual foo part of that method call is known as a message. And in a pure object-oriented environment, that is itself an object. You can actually manipulate that in an object-oriented way. So I'm going to bring to your attention an email by Dr. Alan Kay. I actually have a link here, but I don't know how well. Yeah, you're probably not going to be able to see that on the video. I'll post this document online as well. And basically, he's the person who coined the phrase object-oriented in the first place, and he later regretted this. So he seemed frustrated when he wrote it, in fact. Basically, he writes, just a gentle reminder that I took some pains at the last Uppsala to try and remind everyone that Smalltalk is not only not its syntax or its class library, it is not even about classes. Okay, let that sink in for a bit because that's actually a very important sentence. I'm sorry that I long ago coined the term objects for this topic because it gets many people to focus on the lesser idea. All right, the big idea is messaging. That is the kernel of the Smalltalk and /Squeak environment. That's what it's all about. And it's something that was never quite completed in our Xerox PARC phase. All right, so even back then, that was a work in progress. He wrote that message in 1998, 18 years after the public release of Smalltalk 80. You would imagine that after 18 years of public exposure to object-oriented programming, that this would be something that would be imbued in programmers. But it turns out that's not the case. So we dispense with messages. Aesthetic programming is early bound by default and is late bound only when required. Without the messages and message passing to have to worry about, there's little need to make invoking subroutines, be they functions or procedures, late bound in any way. For this reason, aesthetic programming also dispenses with the idea that everything must be late bound. This gave cause for concern amongst the viewers of this talk last time, because there was some contention over what early bound and late bound actually meant. So I'd like to review that in a bit. We know from Chuck Moore's previous thinking via V. Colorforth that there are three distinct times when developing software. There's edit time, when you're actually composing software for the computer to run. There's compile time, This is when you're actually translating the software into a form more amenable for execution, be that raw binary or some tokenized format, what have you. And then there's actual runtime, right? So this is when the computer actually executes the software that you've composed. And we also know that edit time is cheaper than compile time in the sense that decisions that you make at edit time are decisions that don't need to be made at compile time. And similarly, if you're making decisions at compile time, they don't need to be made at runtime. And that is actually the root of making very fast software. So back to the early binding versus late binding. When is the best time to resolve what I mean when I say dupe? Am I duplicating a string? Am I duplicating a floating point number? Am I duplicating an integer? There's possibly 3 different types of dupes. There could be an infinite number of types of dupes, especially when you're working with an infinite possible array of data types at your disposal, right? So this is where early bound versus late bound distinction comes in to play. If we are working with an early bound environment, the meaning of dupe is known at compile time, and therefore you can embed the reference to the subroutine call, if you will, to the dupe implementation right then and there. You don't have to worry about it anymore. There's no runtime decision making involved. If it is late bound, on the other hand, what you're going to find is that there's code somewhere, somehow, embedded in your program that basically says, okay, what am I duping? Locate the implementation for that proper implementation of dupe, and then call that. In other words, the decision of which subroutine to call is made at runtime, not at compile time. That's the distinction between early bound and late bound procedure resolution. So for a fourth word like dupe, it seems obvious that early binding is the one that's preferable. But there's all manner of operations that you might want to use late bound resolution for instead. Some languages like Python, IO, and Smalltalk rely exclusively on late binding. Others like C and Oberon 2, they have the convention where things which are not specifically type bound procedures, which is Oberon's phrase for these things, are early bound, and those things that are type bound procedures are late bound. So for instance, in C++, a method has to be declared virtual in order for it to be a proper late bound method. So aesthetic programming also does away with no dependencies of, I'm not phrasing this quite right, no dependencies of intentions. Sorry, no duplications of intentions, excuse me. So remember what I mentioned earlier, like if I've got a fourth program and I'm trying to integrate 3 other modules written by 3 other authors, each with a different object-oriented package, whether it be OOF, mini OOF, and so forth. If I wanted to integrate and use those packages, do I integrate those object-oriented toolkits as well? And if so, how do I manage that? Do I write one module in terms of another? How do you debug that? And so on and so forth. Like you'd have to become, it's almost as though you'd have to become familiar with programming 3 different object-oriented dialects of forth all at the same time just to maintain that one program. And that is very clearly burdensome to any programmers who would be involved with that. So we definitely want to minimize those dependencies on that particular thing. So I'm just going to jump ahead here. Aesthetic programming is not a panacea, right? We rely on the self-discipline much more heavily than on other programming techniques. I'm not going to lie about that. I rely on declarative, inquisitive, then imperative programming conventions to habituate this discipline into my own subconscious. So when I write forth, it just kind of rolls out naturally. With only a small amount of practice, you'll find that writing this way becomes pretty much automatic. Per Chuck Moore, things which can happen earlier in the development cycle should happen earlier in the development cycle. Edit time, compile time, then runtime in order of preference. So, how does static programming actually work? So basically, you have these things called entities, right? So one of the nice things about object-oriented analysis, as distinct from programming, is it allows you to think at a higher level of abstraction in terms of that a human can understand. Object-oriented programming literally is anthropomorphization of software in a very real sense. But there's two ways of doing that. One is you can think of them in terms of objects, which are little self-automata, if you will, or you can think of them in terms of entities, which are more passive things. In aesthetic programming, we use the concept of entities. So entities are like objects, but not. They have, we'll get into this in a little bit, but entities have an identity. That is to say, you can clearly say that this entity and that entity are distinct, even though they may have the same value, but they have no locality. That is to say, you cannot take the base address of an entity. There's no such concept. And I'll get into explaining how that works in a little bit later on. Basically, there are two primitives. You have one called entity, and it just returns a new number, in a sense, that is unique to that entity. That is the label that by which that entity will be known. And then there's another word, retired, which declaratively says this entity is no longer valid. Now that you have entities, we're going to move on to relations. Relations ends up working quite well to replace types, containment, possibly even more things that I haven't really identified yet. And that they are intended to be strategic rather than tactical, all right? That is to say that they focus on making correct code, not necessarily fast code or efficient code, that sort of thing. All right, so observe that entity has no idea what kind of entity you are interested in creating. That is to say, when I call the word entity and I get back that number, it has no idea at that time what that entity is going to be used for or who's going to be responsible for its evolution. So once you can identify, then you can start to record facts about that entity. And that's where we get into relations. So for example, consider something as simple as a file in a file system, right? So there are a number of different types of facts that you can maintain about files. They have a name, they've got permissions, there's usually modified and last access dates. But that's not always the limit of what you want to store. Oftentimes in a file, you might want to store additional metadata. What's the file's icon, for example? And many file systems don't have built-in support for that. So you end up needing to layer facades, if you will, on top of the file system interface that hides the complexity of dealing with all that extra metadata for you. So the way aesthetic programming works is by using relational variables in the sense of the third manifesto from Dayton Darwin. Basically, we're maintaining different facets of entities in different modules. So if you need to maintain new information about an entity, you can do so by just introducing a new module. You don't necessarily have to write a whole facade in front of a major API just to be able to seamlessly add new information. If you, I go into a little bit here because I start talking about fragile base class problem. Basically, if you maintain, the problem with maintaining a facade in front of an API is the fragile base class problem, because it turns out that if the underlying API that you're shielding, if you will, changes in any way, say, for example, going from ext2 to ext3 file system in Linux, the mere introduction of a journal fundamentally changes how you are best using that file system. And that can actually cause breakage if you're not careful. The other thing I go into here is I talk about strategic versus tactical programming. Strategic code tends to be very problem-oriented. Tactical code seems geared towards boilerplate. In my experience, only about 20 to 33% of all the classes that I write in object-oriented software, including the ones that I work professionally, they are at only that tiny fraction is really problem-oriented. The rest of it falls under what I call boilerplate or tactical. Tactical code. Things like factories, configuration management, FIFOs and queues and stuff like that. I'm not going to say that aesthetic programming will completely eliminate tactical code, because I don't think that's possible. But I do think that it will balance things out significantly better. In my experience, the code that I write using aesthetic programming tends to be much more strategic in nature rather than tactical. So, as I mentioned earlier, modules typically represent one set of related pieces. How can I say this? One facet of knowledge about an entity. So, for instance, if I were writing a graphical application, a video game, for example, I might have a module that exists just solely to record information as to whether or not something is visible on the screen. And if it's visible, how is it drawn? So here we've got a very small contrived example here. Basically, it's saying if you call it visible, the first thing we do, this is written in declarative form whenever possible. First thing it says is, at this point in the code, we know that it's not visible, right? That's what the -viz indicates. And therefore we make it appear, right? So we know that at the completion of visible, we know that it's visible because we've made it appear if necessary. This -viz, for example, we actually check, is it visible? If it is, we do nothing, right? We actually not only return from -viz, but we also return from the word that called it, in this case, visible. And so it goes, right, with the rest of the code up here. Visible is an inquisitive word, for instance, that basically searches its local database, saying, is this entity known to be visible? And if it is, it will return as necessary. Scratch that since I'm program. I said that you can't take the base address of an entity like you can with an object. And the reason is entities can be associated in any number of relations at any given time. An entity, which of those relations would I take? Change throughout the, throughout the program's run as well. So I could actually conceptually, it's possible to start an entity as representing a file on a file system, and through time evolve it into something that's displayed on the screen as though it were a video game character. This is something that would be unheard of in an object-oriented sense. That's like changing the class out from underneath the object. That's not saying that I recommend you do that, but it is something that is possible to do. Polymorphic, meaning not polymorphic. In other words, the general concept of what the program is trying to do is very declarative and very inquisitive in nature. You express it in terms across all different data types that your program is working with. In program callbacks, there are always the exceptions to the rule, but speaking, if you're doing something which is that entity, 60% of the time, you're going to have something that's actually imperative in nature. So as you're writing, for Oh, no worries. Okay, testing. 1, 2, 3. Testing. 1, 2, 3. Cool. Okay. So now what I'm going to do is I'm going to go through a module which is written using aesthetic programming principles. Basically, you'll see from here, starting at 16 constant max vectors, I declare some state here, internal state, how many vectors are currently allocated, what is the most current and an alternate vector record. These are actually pointers, if you will, to the current record, as you can see by these accessors. Going down further, we actually see the beginnings of the database itself. The database is consisting of 16 up, or I should say up to 16, based on this implementation, vector descriptors, I'll call them. In this particular case, I have one column, which is expressed as an array called vec entities. And in this case, I maintain an array of records. And these records have basically, these are the fields here, you know, buffer length and how big of an allotment I have in the dynamic heap. And I've got, you know, this word 0 vectors, which basically zeroes out this database. Now, in this particular case, I keep vector descriptors in memory, obviously, because that's the fastest possible way of accessing them. But there's no reason why I couldn't keep these vector headers in block storage, for example, in which case these vectors then become orthogonally persistent from the view of external software. The only real difference in performance would be, you know, the persistent vectors would be slower because you have to deal with I/O overhead. But that would be pretty much about it. And that's essentially how the unsuitable blog that I mentioned at the beginning of this talk worked. So that's actually where a lot of this comes from, right? So keeping your data close to you is very important. Now, this is a word here called vector. And as you can see here in the documentation, it says declares that an entity E is parenthetically also a vector. And the way it works is we check to see that it's not already in our database of vectors. We check to see that there's room to, you know, to record the fact that it is a vector, and then we register it. So some things to note, publicly accessible words tend to be complete words or even phrases. Internal words, that is to say words that are local, intended to be local to that module, tend to be more mnemonic. So reg, for example, registers the provided entity ID as a new vector. And the way that it does that is we allocate a new row, and then we fill that row with, in this case, a default allocation of 8 cells. We give it an allocation size of 8 to indicate that. And in this case, I have a previous size field, which I use to grow the vector according to Fibonacci sequence. So I need to know the previous allocation. So in this case, I fake, if you will, an allocation size of 5, so that the next time I grow the vector, it grows it by 5. And it grows Fibonacci sequence accordingly. Here's another internal word, as indicated by the rather mnemonic name that it has. And it's basically an indexed storage operator. And then here we have our declarative words. These are still internal, but they're still fairly declarative. And you can tell this because being that they're guards, their inputs match their outputs, right? You can think of them as filters. That way, you don't have to pollute your code with dupe, drop, swap over, like you can avoid all the stack notation down in the business logic of your code. All that stuff gets hidden away. And in the way we express not present or neg present, we say 0 begin, blah, 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 while not match 1 plus repeat drop, right? So when you read this, basically this is an idiomatic phrase that says, for all vectors in our database, there is no match. That's what the neg match says. So now we have our word neg match, which basically says, for this vector I, ensure that it is not a match. And we do that by actually comparing our first reference to the table here, this right here, this vec entities. This is the first time we actually start touching data. If we do find a match, holy crap, match! Obviously, it's an exceptional condition, right? So we need to handle that exceptional condition right away. And the way we do that is we just exit. Because if the vector is already a vector, we don't need to do anything more to make a vector a vector. I mean, I could literally call one vector, one vector, one vector, one vector, and it's just the same as calling one vector just once. And that's the power of declarative programming there. You'll notice here that in this chunk of code for appending a value to a vector, that I reused the match word. So words that are internal, words that are mnemonic, tend to be overwritten. And this is the value of hyperstatic global environments. This is something that you will never find in Lisp, for instance. The ability to redefine and fully contextualize words based on your semantic environment is something that is unique, as far as I can tell, to Forth. Other languages, they have their own mechanisms, and that's cool. I think that this is a very Forthish way of doing things in Forth. But as you can see here, this is a much more sophisticated chunk of code, because when you go to append a vector, you may have to grow the vector, right? So we express this. The first thing that we do is we check and make sure that we are, in fact, dealing with a vector. The next thing we're going to check is to make sure that the vector itself has enough room to store the item that we're going to store into it. If it does, we'll place it and then we'll exit, right? There's nothing more for us to do. Otherwise, we're going to grow the vector. This is actually where the Fibonacci sequence comes in. And then we'll execute this loop again. Now, this looks like an infinite loop, and technically it is. But through inductive logic, I can prove that this iterates at most once. So there's no fear of recursion, infinite recursion here. So here's the logic for grow. Grow is an internal word, as you can imagine, although it is imperative. And you can tell that it's imperative because it's unguarded. And it doesn't really care what's going on in the environment. It's just going to go ahead and plow ahead with allocating a new buffer, copying the old buffer to the new buffer, computing the new Fibonacci sequence counters, and then updating the metadata in the database accordingly. So this is a very imperative word. Similarly with set, again, no guards. We do make use of an internal word, which I call set element. This one is somewhat guarded in a sense that it makes sure that you're actually dealing with a vector before doing what it needs to do. And yeah, so that basically, already know how plus vector, neg match, and match work. So now we come to the word that gave me such consternation today at SVFIG. That literally took me about 3 hours to get working right. Clone. This is one of the few examples of a public imperative word. This basically creates a new entity. See, we're calling entity there, right? So we have a new entity, but at this point, we don't know what this entity actually is. It's a vector. So we've now registered this entity as a vector. And now we're going to invoke cloned. And in fact, this is actually buggy. I need to insert a dupe. So cloned is actually, I label it as an internal word because I don't intend other people to actually invoke it. But despite the fact that it's internal, it is still a declarative word. Because no matter how many times I call cloned with the same E1 and E2, the end result is exactly the same. Right? So we empty out the second vector. We make sure that our inputs are still vectors, and then we copy over the header, and then we copy over the buffer. The idea is it's a shallow copy of the actual data elements, but it's a fresh copy of the vector. That allows us, for example, to say, for example, if I want to do a map reduce operation, I can clone my input vector, perform my map, which actually works in place, and then I can do a reduction on that vector without touching the original vector's inputs. So it's a little bit less convenient than a functional programming language, but not by much, once you have the full library. And as you can see here, I still have yet to finish the rest of the library, but the rest of the library should, in theory, not take too much time. So this is an example of a module that is itself written in an aesthetic form. And you'll notice several things. One, I use column major storage for internal data that is frequently searched. This is important because this maximizes your cache utilization. I use row major storage for data which is frequently accessed with relation to other fields. And last but not least, so the comment was that it was closer to how the fourth dictionary is implemented. I'm going to give a qualified yes because it really depends on the fourth compiler that you're referring to. But in the case of color fourth and my own fourth for the Kestrel, that's exactly right. The Kestrel fourth actually maintains the word headers in column major format, and then the rest of the stuff is row major. Same idea. So yeah, so basically the other thing is you'll notice that the buffers themselves use dynamic memory management. So not only am I using static memory management inside the module for maintaining the header metadata, I am still using dynamic memory management as well. And I could write this, I could actually write or rewrite this module to use block storage or file storage, however you want to implement persistence. And all the other software that depends on this will never be the wiser because all that detail is kept entirely inside the module. So I've got probably about 8 minutes left in my time slot. So I will open it up to questions. Yes.
Early on, you asserted that one of the challenges, with multiple object-oriented programming packages is bridging the impedance mismatch. Some would argue that this is partially a problem of standardization. If we just agreed on, here's the one sure way to do this, there would be have that problem. Care to speak to that?
So the concern was the issue with specificity to fourth. The concern was the issue of involving 3 different object-oriented packages was one of standardization. In other words, a development organization would standardize on one and only one development package, and or in theory, in a perfect world, the 4th standards committee would say, this is the one true object-oriented package that we should use. My comment to that is I would still prefer to write code aesthetically, but within a module, I would probably use object-oriented programming. I mean, that would still be the case, even with multiple different packages. But not having the key here is not having not leaking the details of your module's implementation across the module boundary is the key to what makes aesthetic programming plug and play, for lack of better term. And it's not, nothing's going to be perfect. There will be times when you swap something out in an aesthetic program and it's like, oh crap, I sure wish I had, abstracted that better, or I sure wish that this, had been written differently. That's just the nature of software engineering, I think. But when it comes to me looking at, for example, Swift4th code, and it's like, well, gosh, I sure wish this wasn't so damn Windows specific, right? Or I wish it wasn't so dependent on swoop, because I don't know what half the features of swoop are. I wouldn't know how to map what I'm reading there into, say, mini oof. Yes.
This is a object-oriented type of programming, which means this stuff here would be more of the implementation type stuff, right?
So the question was, I'm basically doing object-oriented like programming, and this was more of an implementation detail. It has, I would say, it has its roots in object-oriented analysis.
So you're talking about like
Modeling a system, yes. So the idea here is that, like for example, with classical object-oriented environments, you typically have one module per class, maybe multiple classes per module, but we'll say that this is a good first order approximation. But then you look inside the class, and typically you'll find that class is responsible for 3 or 4 different logically related but different things. So for instance, if an object happens to be part of a collection, you might have you might have pub/sub functionality in it. For example, publish subscription methods. Whereas with aesthetic programming, you typically would not have that. So what would happen instead is I declare an entity. So here's like this empty object, if you will, for lack of better analogy. Here's an empty object, and I'm going to declare that this object has pub/sub functionality, right? So I'm going to have a separate module that is focused just on pub/sub stuff. I then say this object happens to represent my checking account. So now I'm going to say in a separate module, here's all the checking related functionality. And then I'm going to say this is a visible object. So not only is it representing my my checking account, but now I can actually see it on the screen, right? These are 3 separate modules that have 3 different levels of functionality, but they're all much more reusable, because now I can take that pub/sub module and reuse it somewhere else, whereas before that pub/sub functionality is embedded in that class file. There's no way for me, except by way of cut and paste, to reuse that in another package, if that makes sense.
Yes, but also mentioned an untitled object. You also mentioned relationship objects. Because that's very important too. That's the one that gives you your what your interface is.
Correct. Yeah, the relational variables, which are basically just relational tables in database speak, they represent the knowledge, the core functionality of what it is you're trying to accomplish. They are, however, slow. So if you're going to make heavy use, if you find that you're making heavy use of full table scans, for example, which admittedly in my code happens quite frequently, but at the same time, my tables are restricted to like 16 or 32 elements. So it's not really going to make that big of a difference. But if you're working in a commercial setting where you've got thousands of rows, you'll probably want to optimize and start using indices. This is going to, this is actually touching on a subject which is part of the family of programming practices that I came up with way back in 2010. Because if you go back and review my project presentation, there's actually 6 items there. And one of them is factoring out the use of pointers, because the pointer is basically the data equivalent of a goto. And you want to make sure that that's well factored out. And the way you do that is through indices. So you can, I can maintain a flat table like this, but if I needed really, really rapid access to any, one of the rows or whatever, I would probably use either a skip list or a B tree as an index. And then that way there I've got, yeah.
Pointers are dangerous. They have to be, remember, one end is pointed.
Right. Yeah. Yeah, it's the data equivalent of a goto, and it's they're useful. Don't get me wrong. You can't program without pointers, and in fact, where am I here? These 3 variables, or I'm sorry, these 2 variables here, the currec and altrec, those are pointers, right? And I make frequent use of them in the module. I do not let those values get out of the module, though.
In C, C++, they would be static. Only known inside of there.
Right. Well, I mean, here they're hyperstatic. Yeah. Go ahead. Yeah. So they're what's called module local. Other people would use this phrase module local, but in Forth community and functional programming community, this would be called hyperstatic. But same idea. It's basically just a way of saying conventionally, these are module local and they're safe to redefine in another module. Yep. Yeah, I've got a link to it at the beginning of my script. So what I'll do, if there's no further questions, because I see that I'm out of time, I am going to take my script. I will commit it to HTML, and then I will post the HTML, send it to Dave for posting.
Post the HTML on whatever website that you have and send me the link to it.
Okay, I'll do that. I'll post the HTML myself, whichever, and then I'll send out a link to the material. And then I'll be happy to answer any questions on the mailing list as well.